Hello, welcome to the presentation of our paper, Optimal Coordination of Electric Vehicles for Voltage Support in Distribution Network. This video is created for IEEE ISGT-Asia 2022 conference. Here are the authors of this work. I'm Xiaoli Chen, graduated this year from the University of Manchester for the master's degree. This research is done with my supervisor during my master's study, Dr. Alessandra Parisio, a reader in the Department of Electrical and Electronic Engineering at the University of Manchester. In this presentation, first I will introduce the background and our contributions. Then I'm going to explain the proposed methods, including the driver behavior modeling and the optimization framework. Next, I'm going to present the case study, and finally, the conclusions. As the electric vehicles and solar generations increase substantially in residential areas, they're causing various problems to the distribution network, such as voltage and frequency fluctuation, harmonic distortions, and so on. Among them, this work focuses on voltage fluctuation issues. To deal with voltage fluctuation, traditional approaches such as on-load tap changes and capacitor banks are relatively slow, and frequent switching of tap changes will also greatly reduce their lifespan. Additionally, due to the low reactance to resistance ratio of distribution networks, both active power and reactive power need to be considered for voltage fluctuation issues. Therefore, the coordination of an increasing number of electric vehicles is an appealing solution. In this work, the active power and reactive power charging and discharging of electric vehicles are all considered. As shown in this figure, it is also known as EV four-quadrant coordination. The x-axis shows the active power charge and discharging. They are done within the batteries. The y-axis shows the reactive power charging and discharging, and they are realized by the converters in the chargers, thus avoiding battery degradation problems. The contribution of this work is that we devised a model predictive control-based framework to coordinate the electric vehicle four-quadrant operations. And as part of the research, we also developed a driver behavior model for each EV driver to simulate their stochastic charging requirements. Different from previous studies, we have all the four factors considered below. We have EV active power, EV reactive power, renewable generation, and driver behavior modeling. The methodology consists of two parts. First, I will introduce the driver behavior modeling method, and then I will introduce the MPC-based coordination. For driver behavior modeling, the method Markov chain Monte Carlo is used. Markov chain Monte Carlo is a method that utilizes both the advantages of Markov chain and Monte Carlo simulation. The Markov chain is a conceptual memoryless chain where the state transits from one to another based on probabilities, while Monte Carlo simulation can be used to generate a number of chains with the given probabilities. In this work, the Markov chain is used to extract the patterns of vehicles' parking time and energy demand. Two states, plugged and unplugged, are defined, and their states' transition probabilities are calculated based on the dataset in two trial projects. Then, Monte Carlo simulation is used to generate the actual behavior of a number of EVs as the input for the MPC-based coordination, which will be introduced in the next slide. After generating all the EV user samples, we developed the model predictive control-based optimization tool for EV coordination. MPC is used because of its ability to both consider the future and adapt to current changes. At each time step, the MPC tool receives the inputs, optimizes the EV operations, and derives output solutions, which are EV active and reactive power scheduling. The input includes the EV driver information generated from the driver model and the real-time grid side information including solar generation, loads and electricity prices, and predictions for the total time window generated based on the normal distributions. Then the MPC model calculates the solution. A twofold objective is formed, minimizing both the cost of all the transactions in the charging stations and also the voltage deviation for all the distribution network buses. After calculation, the tool finds a series of solutions in time sequence with the length of time window t, and only the first solution of active and reactive power actions are implemented, while the rest are discarded. Then I will talk about the case study and its results. The case study is done in a 33-bus distribution network with high penetration of electric vehicle charging stations and solar generations. 4 scenarios are studied, each with different EV penetration level and different EV load distribution among buses.
This page visualizes how the proposed tool coordinates the EV loads. The graphs A and B show the active profile and reactive power profile before and after EV coordination. In Figure A, the blue plot is the base load and distributed generation. On top of that, the pink plot adds uncoordinated EV loads to it. Then the purple plot shows what the pink profile looks like after the coordination of the proposed tool. In Graph B, the blue plot is the base load and the red plot shows how the reactive power from EV changes the overall profile. The graphs show that the proposed tool can smooth the active power profile and provide reactive power support during peak load periods. The graphs A, B, and C on this page show how the voltages are coordinated as a result of EV 4-quadrant coordination. The yellow color shows the profile without optimization, and the purple color shows the coordinated profile with our proposed tool. It can be observed that all the voltages are effectively regulated within the limit. The table presents the voltage deviations optimization for each scenario. It can be seen that the voltage deviations can be improved by 36% up to 90% on different buses.
The graphs A and B on this page show how the active power coordination follows the electricity prices. In Graph B, the blue plot is the predicted electricity price and the red plot is the real-time input electricity price. Comparing the purple plot in Graph A, which is the coordinated total load, and the red plot in Graph B, we could see the coordinated load is effectively following the real-time prices rather than the predicted prices. The table here shows the daily cost savings for all scenarios. It can be seen from the table that the cost savings ranges from about 5% up to about 25%. In summary, the proposed tool can effectively reduce the voltage deviation to within the limit and reduce the total costs for the transactions happening in all the charging stations. The future works. The reactive power from PV smart inverters and traditional voltage regulation tools can be included to be coordinated with EV 4-quadrant operations. Additionally, for the driving behavior modeling, double Markov Chen can be used to further explore the correlation between the parking time and energy demand. Thank you very much for your attention. If you have any questions, please feel free to contact Xiaoli Chen 1999 at gmail.com.